right, and welcome back, everybody. Glad you're hopping over to this session. So, we've been talking about a lot of very interesting collection methods of various kinds of data, and so what we're going to talk about now is what are we doing with all that data? So, this panel is called Data Deluge: Innovative Approaches to Exploit the Flood of Big Data. So this panel is going to examine the big data challenges for science, engineering, operations, and strategic planning, and it's going to explore potential solutions, including the role of artificial intelligence and machine learning and the emerging applications of said data. So thank you again to our day one sponsors, Johns Hopkins University Applied Physics Laboratory, KBR, and SAIC. Our moderator for this session is Mark Clampin. He's Director of the Sciences and Exploration Directorate at NASA's Goddard Space Flight Center. So Mark, turn it over to you.
Okay, so good afternoon, everybody. As you heard, I'm the Director of Sciences and Exploration here at the Goddard Space Flight Center. And the goal of this panel is to examine the deluge of data facing the space and earth scientists and to discuss innovative approaches we can apply to exploit this flood of big data. So we've assembled a panel of 3 young scientists at the forefront of this field to discuss the subject. And I'm going to start off by introducing them. So first of all, we have Dr. Megan Ansdell, who is a program officer in the Planetary Sciences Division at NASA headquarters, where she's currently involved in a variety of programs and activities related to exoplanets and planet formation, as well as machine learning and other data-driven approaches. Before she joined NASA, Megan was a Flatiron Research Fellow at the Flatiron Institute in New York City, where she developed machine learning algorithms and other computational methods for studying young stars and their protoplanetary disks. Megan got her PhD in astrophysics from the University of Hawaii in 2017, and her thesis won the International Astronomical Union's Prize for Planetary Systems and Bioastronomy in 2017. And before her PhD, she also earned a master's in international science and technology policy from George Washington. And the thesis for that particular manuscript won the 2011 Sakharov Prize for Space History. Our second panelist is Dr. Newton Campbell. And Dr. Newton Campbell is a computer scientist who specializes in artificial intelligence and machine learning. He's also a STEM educator and space advocate. At SAIC, he's a principal solutions architect, specializing in AI. And in this role, he currently serves as the senior computer scientist and AI subject matter expert on the NASA Langley Research Center's OCIO data science team. Dr. Campbell's lead researcher on several programs concerning intelligent drone flight, geomagnetism, and high-performance computing for climate science. DARPA recognized Dr. Campbell as a rising star in 2015, and he's also been recognized as a modern-day technology leader by the Black Engineer of the Year Awards sponsored by the Council of Engineering Deans of HBCUs. And finally, our third panelist is Dr. Hannah Kerner. Dr. Kerner is an assistant research professor in the Department of Geographical Sciences at the University of Maryland. And her research involves developing new machine learning methods for analyzing remote sensing data for applications in agricultural monitoring, food security, earth science, and planetary science. And Hannah received her BS in computer science at the University of North Carolina, Chapel Hill, and a PhD from Arizona State University, where she developed methods for facilitating scientific discovery and planetary exploration investigations of Mars, the Moon, and the Earth using machine learning. She's also developed onboard software for a constellation of satellites, a planet, and has worked at several NASA centers, including JPL, Goddard, and the Langley Research Center. So we have a great panel of scientists here this afternoon to address this subject. So let me start off by asking Dr. Ansdell to say a few words.
Okay, thank you, Mark. Can you hear me okay? Great.
Yes.
Okay, so I thought I'd spend my time at the start telling you about some of the efforts going on at NASA that are aimed at exploiting this flood of big data, as well as bring to your attention some of the current and future opportunities that we're providing to the community. So there's been a big push at NASA over the past couple of years to better enable open science. And a few years ago, NASA established the Strategic Data Management Working Group, or SDMWG, which produced a report called the Strategy for Data Management and Computing for Groundbreaking Science for 2019 to 2024. So that's a bit of a mouthful, but I encourage you to read the report. The overarching purpose of the document was to basically set up a framework for enabling open and groundbreaking science through the continual evolution of NASA science data and computing systems. And it recommends doing this by establishing and leveraging partnerships across academia and government and private industry, including internationally. So this report established priorities for the first 12 months of its implementation, which has resulted in a bunch of efforts being rolled out over the past year. So for example, there was a new open source ROSES software element in 2020. So ROSES is the major annual solicitation that NASA puts out for basic and applied research proposals. And in 2020, there was the first cross-divisional ROSES element called the Open Source Tools, Libraries, and Frameworks, which focused on funding projects aimed at improving and sustaining existing high-value science software. So I think you'll continue to see these types of funding opportunities coming out from NASA Science in the future for supporting open source software development, which I think is something that is sorely needed in the community and can help us with this big data problem. So other activities out of the SDMWG in the past year include the initiation of cross-divisional prizes and challenges, the hiring of an S&D data officer, the establishment of an S&D-wide standards group, and the reinitiation of internal brown bag discussions. Additionally, the SDMWG established an AI/ML working group that I am currently a part of at NASA headquarters. So this working group is composed of representatives from each of the Science Mission Directorate divisions. So I represent Planetary, and there are also individuals from astrophysics, earth science, and heliophysics, as well as the high-end computing group. So we've been tasked with basically assessing the current AI and ML capabilities within each NASA science division, and then to identify and help accelerate the possibilities of AI and ML to support NASA science. And there's a very strong focus on cross-divisional collaboration in these efforts, which is why our working group is composed of members from each of the NASA science divisions. So our working group will, of course, produce a report, but we've also been carrying out various activities as we gather information and engage with the community. So one of the first things we did was solicit cross-disciplinary use case project demonstrations. So these were relatively quick demonstrations of AI and ML to address the needs of multiple NASA science divisions. So we funded several PIs with a total of about $500K to complete these projects on timescales of a few months. The projects are wrapping up now, and one of our other panelists was one of these PIs, and I think she might be sharing some of that work today. We also just completed a community-wide survey to assess the level of AI and ML knowledge in the NASA science community, as well as gauge attitudes towards AI and ML usage in science research to better understand the potential challenges going forward. So this survey just closed a few days ago, and we had a great response, something like 450 submissions to the survey with fairly even coverage across the different NASA science divisions, and we'll be including a detailed analysis of that survey in our report. We're also hosting an inaugural 3-day workshop in a couple of weeks, bringing together leaders in AI and ML usage across NASA and academia and industry, including Google and Facebook. And this is basically to instigate discussions on more big picture strategic directions for the application of AI and ML to NASA science. So this will hopefully be the first in a regular series of strategic workshops that the community can engage with. And if any of that sounded interesting to you, we recently submitted a session to the American Geophysical Union, or AGU, fall meeting on multi-party cross-divisional AI and ML uses for science, which will hopefully be accepted. So I encourage you to look out for that and submit an abstract to that session. So that's it for me. I hope I provided some useful information for the types of opportunities coming out of NASA on the topic, and I'm happy to talk more about any of it.
Okay, thank you, Megan. Next, we'll hear from Dr. Campbell Newton.
Hi, thank you, Mark, and thank you, Megan. I thought that was an absolutely wonderful breakdown. I think we have a lot of places where some of our work intersects. So in that introduction that you heard Mark give, one of the things that he talked about is the fact that I work with the Langley OCIO data science team. We're basically a group of subject matter experts in artificial intelligence and data science that go around both Langley and around the agency, working with scientists, engineers, and even folks at the enterprise level to help them adopt the latest advances in artificial intelligence and machine learning. So one of the things that I'm going to talk about today is a couple of the bit more in the weeds projects, just for a couple of minutes, that I'm working on, as well as things that we're doing to help out at the enterprise level at NASA. So my primary project down at Langley right now is focused on the urban air mobility problem. There are a variety of challenges that are posed by UAM operations. Currently, contingency management in that regime is just seen as a highly prescribed rule-based approach. And under ARMD, the Aeronautics Research Mission Directorate, we have what's called the Intelligent Contingency Management Program, where the goal is for us to give the newer vehicles in urban air mobility, think LA-8, think Lift Plus Cruise, some of the electric vertical takeoff and landing vehicles that are being proposed to fly around cities in the United States, and folks are looking at flying around the world, taking some of those vehicle models and seeing how we can effectively allow the vehicle to form its own contingency plans, to form its own plans for getting out of an emergency. So in my current work, we're focusing on a tool set that does just that. And one of the benefits of doing that work is that I'm working with a number of aerospace engineers, both at Langley and around the agency, who are getting to know more about artificial intelligence. Part of the program is, yes, developing those capabilities, but the other part of the program is the educational aspect of it. We have so many conversations back and forth where we're using artificial intelligence and machine learning terminology back and forth, and are educating each other in both regimes. And in terms of overall adoption, that's kind of the benefit of the data science team at Langley, is that we're reaching out to folks that are brilliant subject matter experts in these other fields and getting a chance to work with them, having them truly understand what some of these AI applications are about, and then based on their understanding, instituting something that actually is practical, that's actually pragmatic, that goes beyond a simple example in a paper. We're really building this stuff to actually fly in vehicle models. We have a number of private and public industry partners that we're working with to do just that. The second major project that I'm working on, that again is a little bit more in the weeds, is we're looking at the space radiation problem. So this is about 6 different sites together under the Human Research Program, operating on a program that's called the Translational Radiation Research and Countermeasures Program. So as most of the conference attendees know, NASA's human lunar exploration plans under the Artemis program call for sending the first woman and the next man to the surface of the moon by 2024 and establishing sustainable exploration by the end of the decade. But all of this, that entire journey is predicated on the notion of our astronauts surviving and sustaining relatively small side effects from space radiation. Space radiation consists primarily of ionizing radiation, small but high energetic particles, and there are 3 naturally occurring sources of space radiation: from trap radiation, you have galactic cosmic rays, and you have solar particle events. And except for the Apollo mission, most of NASA's human spaceflight missions have taken place within the cocoon of the Earth's magnetosphere. So what our research focuses on is how to take just about everything we've learned in that cocoon and use machine learning, use artificial intelligence to extrapolate it to understand how radiation will affect our astronauts. We're going to do that by translating radiation research results to humans using bioinformatics and computational modeling to link previous data generated to new sources of space relevant radiation exposure and new animal models, including human medical radiation exposure. So this is an example of us taking data both internal to the organization, things like Gene Lab and the like, as well as external data, using a combination of machine learning capabilities as well as subject matter experts in the space radiation field, and trying to pull as much as we can from that data to apply it to this new regime. And it will be an ongoing effort. So those are two sort of in the weeds projects that I'm working on right now. But I'd be remiss to discuss the things we are working on at the enterprise level, particularly on the data science team. Right now, my boss, Ed McClarney, and others around the agency are leading the design and requirements gathering of an enterprise data platform for the agency. The idea behind this platform is that it's being designed to elevate the agency's ability to seamlessly find, harness, and translate the abundance of data into actionable insights and greater scientific discovery. Right now, the current state of data platforms around NASA is there's no comprehensive search capabilities. There are, and every NASA person is going to grow when they hear this, there are a bunch of siloed data sets all around the agency. And and all of the analytics environments are localized. And there are a number of other problems, but those are some of the main key ones. What they're trying to get to on this enterprise data platform effort is through a combination of enterprise class platforms and machine learning talent is to introduce self-service search based on the current state of the data sets, getting faster answers with a catalog of data sets rather than trying to go out and search different data sets independently, consolidating some of the data that we have here at NASA, and optimizing analytics processing, but not just through a single platform. The idea here is to avoid vendor lock-in and allow the flexibility of using different platforms in order to do just that. So there's this larger enterprise data platform effort, as well as a number of smaller efforts that I and others have been working on in the data science team. For instance, for platforms that avoid vendor lock-in, platforms that allow for that effectively allow for the quick finding of research of the data behind published research and the like. So we're working on addressing some of these problems independently on smaller efforts, but the idea is to bubble those solutions eventually up to a larger scale platform like this. So happy to take answers on any of those things or answer questions on any of the other efforts that we're working on the data science team.
Okay, thank you, Newton. And finally, Dr. Kerner Hanna, would you like to speak?
Thanks. Yeah, I'm actually going to share a couple slides. Somebody had to do it. As was said in the introduction, I'm an assistant research professor at the University of Maryland in the Geographical Sciences Department. And my background and my research is really focused on machine learning. And in particular, how do we take these massive amounts of data from Earth observation satellites or other spacecraft, maybe observing other planetary bodies, and turn them into actionable insights for scientists or real world stakeholders. And the majority of my work falls under this program called NASA Harvest, which is NASA's applied sciences program on agriculture and food security, for which I'm the AI and machine learning lead. And so here is just some kind of examples of the kinds of products that we produce using machine learning with satellite data as input. So here on the bottom left, we have a cropland probability map of Kenya. So we want to turn these satellite observations into maps of where crops are growing so that we can use this to forecast yields, look at crop conditions, forecast shortfalls, help governments to assess their food balance sheets, inform trade decisions, etc. Up here on the right is what would be called a crop type map. So this is a map of where the machine learning models think coffee is growing in a province in Brazil. And then we also do a lot of work on, how do we come up with innovative ways to create ground truth data sets, which our models rely on so much for telling us what it is we're actually seeing in the satellite imagery. We can't exactly look at an image from the satellite and say, oh, that's maize. Usually we can say it's a crop, but we don't exactly know what type of crop it is. We don't know if it's affected by pests or disease, the conditions, all kinds of things, not just for agriculture, but for land cover analysis and a lot of earth science applications in general. We need this ground truth data. And so here you're seeing the results of bounding box detection from an image from a GoPro that's mounted on a car driving around Kenya. And our machine learning models are detecting where the crops are, in this case, sugarcane, detecting the individual stalks. And then we figure out how far away those crops are from the car so that we can move our point to be on the crop so that we can pair it with satellite images, instead of being on the road, which is where the camera would be. So that kind of is some fun examples of what we're doing. The other part of my work that I especially did during my PhD was, or still continues to be, in planetary science and planetary exploration. And so a lot of times on other planets, we're not so much making these dense maps of land cover like with crop type mapping, for example, but maybe we're looking for certain objects on the ground like craters. We want to automatically detect where hazards are for doing, terrain relative navigation, things like that. And we're also working on, I have a partnership with JPL where we're working on doing novelty detection or outlier detection in rover images to enable onboard automatic target selection based on novelty. So the idea there is that the rover, considers what's in the current frame that it's seeing in its camera and how that compares to what it's seen in the past on its drive, and then makes a decision about what's the most interesting thing in its view to potentially follow up on with other instruments. And then, bringing all of these planets together is this project that Megan mentioned, where we have a project with SMD's working group for cross-divisional use case demonstrations of AI at NASA, where we're looking at creating a domain agnostic system for outlier detection, very much the same algorithms that we're using for doing this target selection on board the Mars rover, we can also use for detecting early signs of disease in a field, in a satellite image. And so that's really the goal there, where we are creating this system called Dora the Explorer, which is domain agnostic outlier ranking algorithms. And we're doing these demonstrations of outlier detection or novelty detection on Earth, Mars, and in astrophysics catalogs, galaxy catalogs. So more results to come from that soon. But I'll just say too that a lot of the work that I'm doing really falls into, I think, these key questions and really this overarching theme of how do we make machine learning work for the real world? A lot of machine learning research focuses on these benchmark data sets that look very different from the world that all of us see in our NASA science data sets or, engineering data sets. And really there's a pretty big gap between using these methods off the shelf and, as Newton was saying, actually putting these things into production, using them to reroute aircraft or do, time sensitive real world applications. And so these questions that I'm often looking at are, how can we create accurate machine learning systems for sparse, heterogeneous labeled data sets? We maybe have a few examples here or many examples there. They all have different formats, different kinds of labels, different cameras, all kinds of heterogeneity in the real world that we need to cope with. And Number two, how do we triage or prioritize this deluge of unlabeled planetary data? So, in especially remote sensing, Earth observation, we have a huge amount of unlabeled data that we want to make use of. And I think that's very much untapped at this point. And number three, how can we create large public labeled data sets in a scalable and affordable way? An emphasis on the public here, because this is also a huge gap, I think, in our area of applications of machine learning, where we have a huge need for more publicly available data sets that the entire NASA and research community can make use of. And so just a couple of examples here on the right, I've showed an example from this on the last slide where we're detecting the crops in these street level images. And so this is one of these ways that we're trying to create these scalable, low cost data collection efforts that we can use to generate public data sets about land cover with georeference information. So we can use this from these street level images from GoPros. We can collect images from Google Street View, which has already collected for us. And we're also looking into crowdsourcing based on smartphone images or even location messages in WhatsApp for areas where we don't have MMS or multimedia messages. And then down here is another planetary example where we're actually, we've done a lot of work to test these outlier detection or novelty detection methods and other kind of data triaging approaches with the PDS image team at JPL. And so the plan for PDS-4 is actually to be able to allow users to search the image databases by novelty or similarity or these other kind of more useful search criteria rather than just what was the most recently collected. And there's actually already some demonstrations of this on the PDS Image Atlas now. If you go on there, you can see, for example, you can sort, you can filter through the high-rise data set to find all the images with craters or all of the images with slope streaks, things like this to help reduce the amount of effort required to go from the archive data to an actual machine learning solution. So that's it for my opening remarks, and I'm looking forward to the discussion.
Okay, thank you, Hannah. So I'm going to kick off by asking the panel first question, and then we welcome questions from the audience. So my question addresses the issue of the best approach to big data problems. So I always think that science should really be driving the solutions. But given the number of applications and work being done out in both the science community and also in other areas like Google and Amazon Web Services, how can we best leverage that to maximize the return of our science data? Does somebody want to take a shot?
Sure. I guess I would say that I think there's a lot that we can kind of learn from existing approaches. Like, these are definitely not different worlds. A lot of the research that's being done are very similar, being done for, like social media, detecting your face from, you guys can't see where I'm pointing, but detecting all of our faces from all the other faces in the world, is not so different from detecting a body of water versus a type of tree. But in other ways, it is so different because of the kinds of data that we're looking at. We have changes through time. The Earth is always changing. Of course, people are aging as well. And so maybe there's a little bit of that there. But, a lot of what we're looking at is very large, like way larger data sets in terms of the amount of data that we're getting over an entire planet every day. But also, we have these additional dimensions of the electromagnetic spectrum, not just RGB data, but many other bands or regions of the spectrum. We have many different kinds of instruments that need to be fused. It's not just like off-the-shelf cell phone cameras. We have this time dimension, as I mentioned. And so, I think there's kind of a trade-off there, where we can't expect the current, commercial machine learning companies or research groups to have solved all of our problems, but we can still learn a lot. So I think there are a lot of opportunities for creating, integrated partnerships with these companies, and especially through programs like Microsoft AI for Earth, for example, that provides a direct conduit between researchers in earth science to machine learning researchers at Microsoft who know enough about earth science data to know those nuances. And so I think that, having more of those direct conversations and continued conversations and collaborations will have the best result.
Just to chime in, so I think that was absolutely a fantastic answer. I think one of the things that I've really learned over the last 4 years is it really does take getting some computer science talent in the same room as some of the folks that are actually doing the science. In terms of what Hannah was saying about, these commercial companies can't predict every single scenario that any of their AI algorithms are going to be used for. So it really does take getting computer scientists into the same room with some of these subject matter experts to really design a data infrastructure that will be amenable to doing science where you may not even know, have foresight into the oncoming results. But a key thing, leveraging what Anna said again, in terms of that, is talking to each other. One of the things that I've noted that, sort of across the industry is that we do need to do a better job of teaching computer scientists how to actually convey some of the results that are being produced by artificial intelligence. That's one of the main things that I've been focusing on, both from a mentoring standpoint as well as just on some of my projects, is conveying what is artificial intelligence actually doing when we're working on some of these projects, when we apply some of this data to, whether it's space radiation data or whether it's flight data, being very deliberate in the message of what artificial intelligence models are doing, why they provided the results that they've provided, and yes, in some cases they're providing unintelligible results. But if you have people that understand the algorithms enough to teach and convey that message, you're going to end up with better results.
Yeah, I completely agree with everything that was just said, and especially this idea of needing the scientists and the machine learning and AI experts to be in constant communication. So I learned my machine learning skills through the NASA Frontier Development Lab, where they literally sat us planetary science down with PhDs in machine learning for 2 months straight, and we sat at the same desk every day. And I think that was great because you learn about the opportunities that can be available by applying machine learning and AI to science, but also the limitations. So, scientists often want to not just take the output of a model, but take that output and, translate it into an occurrence rate of exoplanets or something like that. They want to do some science with it. And I think it's really important for this constant communication between the scientists and the AI experts, so that we understand sort of what we can do with the output of a machine learning algorithm and how that can translate to science, or how it could not translate to the science that you want to do.
Thank you. So let me ask you another question. One of the trends, I'll give you an example I see in astrophysics. We're about to, in a couple of years, go online with a telescope that's going to produce millions and millions of transient events per night. And to ideally follow those up, we're going to need to sort of have AI or ML that can kind of roam across databases in different agencies, DOE, NASA, NSF. Are we ready to do that kind of follow-up to sift, say, 6 million events in a night down to the crucial 2 or 3 you want to look at with James Webb the next week?
from a computational standpoint, do we have the power to do that? Yes. From the data fusion standpoint, that's where we start to run into trouble, right? You know, getting access to all of the data necessary. I mean, going back to the siloed data sets problem, I mean, that fundamentally is one of the agency's big problems, right? And then extrapolate that out to getting data from other agencies like DOE and whatnot. It generally makes that problem even more difficult. One thing that I've found to be very helpful is trying to get in touch with any potential stakeholders like that far ahead of time, and starting to define a data infrastructure that can do that. The other thing that I've recently found extremely helpful, and we're doing this right now with the Calypso satellite and a bunch of coral reef data that's in a number of different data sets, from NOAA to open source data sets, is actually leveraging the machine learning community to help out with some of the nascent problems there before we even get to the point where we want to have a project or a program that really does pull that data together. We are in our data science team at Langley, we're going to be partnering with Georgia Tech. They have an open practicum every semester with a bunch of their Masters of Science students in data analytics, in which you can propose a problem and basically judge the student's execution of a solution to that problem. And so what we're doing in the fall is we're handing them a ton of these open source data sets and saying, hey, identify the problems and give us examples of fusing that data together in order to allow this is coral reef data that we're looking at, to allow us to have a ground truth database of fused coral reef data so that we can match that against some Calypso satellite data. Now, are they going to get to a concrete, hard-nosed, put in production solution? No, but through that sort of crowdsourcing, using university students who want to work on some awesome NASA work, we're getting a lot of the enabling technologies discovered that way. And so that when we do decide to take that project on, we'll have sort of surveyed the space of what's out there. What are the major issues in terms of fusing together these data sets, and what are some of the enabling technologies that we can use? So this is really an area where you can leverage universities all over the place to help you out here as well. Other thoughts?
Megan, did you have a thought on this one?
Yeah, I would definitely agree with the statement that we're computationally ready, but not sort of data accessibility and organizationally ready. But I'll also add that I've been very impressed with all the conversations happening within NASA and the NASA science community at various levels, recognizing that this is a problem and doing things to prepare for it. So I'm pretty hopeful that we'll be ready for when the time comes, and that the work is being put in now to get there.
Yeah, I totally agree. And I think, especially in the astrophysics community, there's been a lot of work in the last several years to prepare for this very moment, right? Where there are many papers in astrophysics using machine learning to find these anomalies or these transient events or things like that. And so, like, from the data or computational, or sorry, from the methods or computation perspective, as Megan said, like, probably we are there. But to give you one statistic to think about, I read one study that said only 22% of companies that say they're developing machine learning models actually have deployed a machine learning system. And that's like in industry, and so I would say that probably in science is much lower. And so I think that just really emphasizes the difficulty of going from results in a paper to an actual system that is running in real time. There's so many considerations from, combining all these different data sources, getting them actually into an ML ready format and into the models, but then also, monitoring that system over time, detecting domain shifts or all kinds of things that are required for continuous systems.
Okay, thank you. Jim, did you have any questions from the audience?
Glad you asked. Yes, yes, we do. So let's start off with this one. To put it simply, how do we keep up? So lots of big data companies that we've talked about, Alphabet, Amazon, all those guys are moving forward at such a blistering pace. How does NASA and the scientific community keep up with that? What are the steps?
So I would say, partner with them. So, and it's not hard to do. So as I mentioned, there's a workshop that we're going to put on in a couple of weeks, and there are people from Google talking about that. The NASA Frontier Development Lab program partners with Google and a bunch of other industry groups to fund research. Like, they're very excited to participate in science. So I don't think we need to keep up. I think we need to partner with them, and they're very engaged. So
definitely. And I would also say that you may not always need to have the cutting edge method. I think there's a lot of, especially in machine learning today, like we see so much sensationalized, like, there's deepfakes now of earth science data, or do I need to use a GAN? Things keep coming out, and I think scientists are thinking like, oh my gosh, what is happening? What does this mean? How do I keep up? But a lot of what we find in especially earth science or a lot of other NASA applications is like, you don't need that super deep giant inception exception architecture, and thinking about like, what is your data literally, and what are you trying to find, and what kind of method do you need to do that, I think can really help you figure out, not, do I need the latest thing, but what sort of method do I need? Yeah, start simple.
100%, Hannah. I ran into this problem. We were shopping around a digital transformation idea that I think we're pushing it to Langley, but we were shopping around Goddard and headquarters. The idea here was to basically the problem is we're not able to tie NASA data to actual NASA publications. We can tie all of our public data and things like that, but the data behind a lot of the papers, it's usually sitting on someone's laptop. It's usually sitting on someone's desktop or something like that. The data that actually went into the graphs. So we started talking about the technological solution for this, and immediately, bless these folks, but for some folks, immediately the solution was, we have to design a search tool that can search around SharePoint and intelligently crawl through data sets and isolate the data that's in our papers and match it up to the papers. Wow. The solution is just to store the data and link it to the paper, right? Like that's all the solution that's needed. But when you start going down this rabbit hole of Google Cloud Platform, Amazon AWS, Microsoft Azure, when you start to look at everything through that lens, everything is starting to become a machine learning nail, right? Right. And so we have to think about what exactly are the solutions, and we probably shouldn't think of it as machine learning trailing behind the science problem, but machine learning kind of an intelligent assessment of whether or not machine learning is actually a solution to the science problem, because it doesn't always have to be. And you do need people in the room who are going to acknowledge that. Sometimes there is a simple answer. Before 2010, we solved a lot of problems at NASA without some of the latest and greatest technologies in machine learning. So it doesn't have to be a solution to everything.
Thanks, Newton. Jim, another question?
Yeah, sure. So it's an interesting point. So we've talked about people in the room, right? You guys have mentioned that. So when we look at the collaboration, the partnerships, the analysis of all this, who isn't in the room now that should be? Who is missing from this conversation? Anyone?
Anybody want to take a shot at that one?
I mean, there are some existential things that I could talk about. There aren't enough women in the room in computer science, et cetera, et cetera. But I do think that when we just in terms of across the board at NASA, we tend to get a lot of customers within the LARC group. I call them customers. We're an internal agency group, but we tend to get a lot of outside folks coming to our group saying, hey, we have this machine learning idea, and no one in their group really has much context about machine learning or artificial intelligence, right? So you're going to want to have, if you're even starting to think of a solution for a massive amount of data that you have, or data that needs to be interpreted, it's important to have computer scientists and technologists who actually understand the matter and can communicate that are those artificial intelligence capabilities, the current state of artificial intelligence in the room, because a lot of the time these folks will come with notions that they received from a conference or from articles in machine learning that we then have to quell and say, well, this is what you actually can do, or this solution is much simpler. You may not even need this, like Hannah said, this crazy GAN or machine learning mechanism. So those, I would say those are my two answers. Existentially, more women and diversity in the room, but from a more concrete standpoint, if you're dealing with technology, have technologists at the idea's inception, because they will, they'll put to bed a lot of for lack of a better term, naive assumptions.
Yeah, I would add to Newton's first point that, it's not just in terms of like, absolutely, we have huge disparities, especially in computer science, in gender representation and racial representation, that we very much need to solve. And I think we also have more like geographical lack of equity in terms of who is doing this work. I think especially for machine learning plus Earth observations plus sustainable development goals, which is like a huge area of interest and research and really like grant money, not just in the US, but for global programs and driven by a lot of commercial funders. A lot of that work is being done by a few research groups in the United States. And so we're doing a lot of collecting data from different parts of the world and using those data to generate research outputs and win more awards. And those awards go to our institutions, and there's not a lot of those awards going to, the institutions in the countries that we're reportedly solving these problems for, and collecting the data from. So I think there's a lot of need for us to be doing international collaborative projects, but also, always thinking about capacity building in these projects that we're doing. I think within Harvest and the NASA Surveyor program, this is a big focus point where, we're not just going and developing some products and selling them to a country or something. We're, trying to go in and actually like train people to do the work themselves and be able to transfer these capabilities and systems to them so that, people can generate their own machine learning models in the future and do these, create these systems themselves. And a lot of what goes into that is being mindful as we're developing these systems of what the computational resource availability is. I never think about downloading a huge data file here in the United States, but for my colleague in Uganda, the data is limited. You're paying per gigabyte, and so it's a totally different way of developing these solutions sometimes, and thinking about how we develop operational solutions that I think we can keep in mind, to your point of who's not in the room.
Yeah, I think what I'm hearing here as an overarching theme is that what the people that are needed in the room are the people who aren't necessarily the ones who have the time or want to actually be implementing these machine learning models. We need to include broader sort of the cross section of the community, I think, in the discussions. And a manifestation of that in my job that I come across is trying to find reviewers for work that uses machine learning and AI. You see this also with publications as well. There's just a shortage, I think, of people that really have the expertise versus how much sort of research is being proposed and publications that are being submitted. So I think another group of people just needs to be sort of like a general education of the community of what machine learning and AI can do. I think that would help a lot in terms of sort of protecting scientific integrity as we go forward.
Thank you. Jim, did you have another question, or?
Well, yeah, so it's kind of related to that. So where do NASA and or the United States stand in comparison with the rest of the world as far as just management of big data? You know, are we keeping up? Are we lagging behind? You know, Megan, you were just talking about it, kind of.
Yeah, I mean, I don't think we're lagging behind. I do think, you know, we can do a lot better job in it as well, though. I don't know. The other panelists might have a better idea of comparing internationally, especially on the science side.
At least from what you know, most of the international space that I talk to are with French and Australia, and as Australia's coming up in their with their very new agency, you know, I think it's only about 3 years old at this point. They do have a data roadmap and a digital transformation roadmap, one that's kind of tied to the rest of their roadmap. So one thing I've seen them do is say, we have our Earth Sciences roadmap, we have our data roadmap. Here's a mapping of the milestones that we have down here in data science and digital transformation to Earth Sciences or to astrophysics, things like that. I'm hard pressed to think that that many places have significantly better data infrastructure than the United States. However, I mean, there are plenty of places that are comparable, but I'm hard pressed to think that there's any place with something significantly better.
So Newton, let me pose this question then. So given that, I was recently on a panel discussing the future of quantum technologies, and the biggest challenge there wasn't developing the technologies from where I sat as I was listening. It was developing that next generation of scientists so that they would be, you know, they would have the qualifications they needed to actually use and develop the technologies. And I wonder where you guys think we are in terms of AI, ML. Are we doing enough to, at the university degree level, to educate all of our scientists across all disciplines in how to use these techniques, or is that an area where the US needs to pay more attention?
So computer science has definitely changed since I've been in school. I mean, the students in, I would say, middle school, when volunteering at schools in the local area, can program at about the level I could program when I was in college. And that's for not super well off middle schools either. So we're doing a pretty decent job, I would say, there in terms of teaching program. In college, there are data science courses, there are artificial intelligence and machine learning courses where they are learning some of these more advanced techniques. I think one issue that computer science has, and that it's struggling with across the board, is that it's still such a relatively young field. However, the amount of sub areas to that field have kind of exploded, and there does need to be a split. And you've seen certain universities split the computer science program into different ways. There are universities with specifically a data analytics program versus a computer science program. There are universities with a software engineering program versus a computer science program. I really like that split. That's what should go for most universities. But there hasn't been a very strong consensus on how that split should occur. But as far as the techniques go, I would say that folks are learning the techniques, and there are just certain techniques that we don't know, how they're going to pan out. Going back to your quantum computing example, we could come across some finding that actually enables quantum computing that no one ever thought of. Right, like that's very much a possibility in the next 10 years. So it's hard to teach some of those items, but you can teach some of the basic theory right away. And a lot of universities that I've seen and talked to, that's one of the sub areas. Even I did that during my PhD. Other thoughts?
Yeah, I think as a professor, I see a lot of students, and I work with students all the way from high school to PhD, and they are excellent. I think the students coming out of universities in the United States are really, really good. And like Newton said, especially in computer science, like my high school students are very advanced and are co-authors on my papers. They're excellent students, but I think maybe what we're not doing such a great job of is creating opportunities for those students to have careers in NASA or in other government agencies or even in academia. I think a lot of the students want to go find opportunities in industry. Of course, the salaries are much, much higher at these tech companies. But I think, cultivating that talent through a pipeline after they graduate and keeping them, or not even keeping them, but attracting them to work on these interesting projects and, still providing them opportunities for growth in a machine learning or other technical setting is something we could probably improve on.
Thanks. So Megan, did you want to have the last word? We're just coming to the end of our hour here.
Yeah, I guess I'll just say that, I agree with everything that was said. I think things are moving at a very fast pace. And also there's a little bit of a disconnect, as Hannah said, between sort of, what the skills that younger people are learning and the opportunities that are provided, I think, in academia and in science. So I'm hoping to see more, solicitations coming out of NASA, like that open source software tool. We can communicate to the community that we're valuing these skills and provide them the funding to do their work.
Okay, well, thank you very much. I'd like to thank the whole panel for a pretty interesting discussion. I think that was great. So thank you very much, everybody. And Jim, I'll hand it back to you. Thank you.
Excellent. Yes, thank you so much, everyone. That was awesome. That was illuminating, to say the least. So thank you again. Thank you very much, Mark. And thank you to our sponsors of the day. We appreciate it. I'd also like to specifically thank, since we were just talking about students a lot, I'd like to thank L3 Harris. They're our education sponsor for this event, and they sponsored 10 student registrations for the event. And we have actually about 25, 30 students listening in, so good to have them on board. So with that, we will now move on to our next session, which is our first Goddard Plus, which is a bit of a shorter keynote talk. Please click over to the next Goddard Plus with Karen St. Germain. Thanks, everybody. Oh, and here's a quick video from SAIC before we go. Sarah, if you could run that.